Every computer you use today, from your smartphone to giant supercomputers, runs on tiny pieces of information called bits. A bit is pretty simple. It can be either 0 or 1. That's it. No maybe, no I'll decide later, just 0 or 1. Now this simple system has worked amazingly well. By combining billions of bits and billions of transistors, we've built computers that can play games, stream movies, generate cat videos, and somehow still remind us to update our software at the worst possible moment. Modern processors can perform billions of calculations every second. That's incredibly fast. But even the fastest computers have problems that make them sweat. Imagine you're trying to find the perfect route between thousands of cities, simulate a complicated molecule, or solve a puzzle with trillions of possible combinations. For problems like these, the number of possibilities grows so quickly that a computer starts feeling like a person trying to count every grain of sand on a beach. Sure, you can add more processors, you can add more memory, you can even build a bigger supercomputer. But sometimes that's like trying to win a Formula One race by adding more shopping carts. The problem isn't that classical computers are slow, they're actually brilliant at most things. The problem is that some challenges become so ridiculously complex that even powerful machines run into practical limits. So scientists started wondering, what if we're solving these problems the wrong way? Instead of using bits that must be either 0 or 1, what if we could use the strange and sometimes downright weird rules of quantum physics? And that idea led to something that sounds like science fiction, but is very real: quantum computing. In the world of classical computers, life is pretty simple. A bit can be a 0 or a 1. It's like a light switch, either on or off. No drama, no confusion. But quantum physics looked at this system and said, what if we made things a little weird? Meet the qubit, the quantum version of a bit. Now, a qubit can still be a 0, it can still be a 1. But here's where things get interesting. Before we measure it, a qubit can exist in a combination of both 0 and 1 at the same time. This strange state is called superposition. Imagine spinning a coin. When the coin lands, it's either heads or tails, but while it's spinning, it's not clearly one or the other. A qubit behaves a bit like that, except much, much stranger. Now, this doesn't mean a quantum computer magically tries every answer at once. That's a popular myth. What it does mean is that qubits can represent information in ways that classical bits simply can't. And that's where quantum computing starts to gain its power. But here's another surprise. A qubit isn't just a tiny magical particle floating in space. Engineers actually have to build real physical qubits. Different companies and research labs use different approaches. Some create qubits using tiny superconducting circuits that look like miniature electronic chips. Others trap individual ions, electrically charged atoms, and control them with lasers. Some use particles of light called photons, and others use neutral atoms suspended and controlled with incredibly precise laser systems. Different technologies, same goal. Create a physical object that follows the strange rules of quantum mechanics. So while bits are the building blocks of classical computers, qubits are the building blocks of quantum computers. And as you'll see next, building and controlling these qubits is where things get really interesting and really cold. So we have these amazing qubits, but where exactly do they live? If you're imagining a futuristic glowing machine from a sci-fi movie, you're surprisingly close. One of the most common approaches today uses something called superconducting qubits. These qubits are built onto tiny chips that look a bit like regular computer processors. But unlike the chip inside your laptop, these chips need a very special environment to work. And by special, I mean ridiculously cold. Really cold. about 273 degrees Celsius below zero. That's colder than Antarctica, colder than the Arctic, and even colder than most of outer space. To reach these temperatures, quantum computers are placed inside giant machines called dilution refrigerators. These refrigerators look less like kitchen appliances and more like giant golden chandeliers hanging inside metal cylinders. Deep at the bottom of this cooling system sits the quantum chip, carefully protected from heat, vibrations, and electrical noise. Because here's the problem: qubits are incredibly sensitive. A tiny disturbance from the outside world can knock them out of their delicate quantum state. Once the chip is cold enough, scientists need a way to control the qubits. And surprisingly, they do this using microwave signals. Think of these signals as extremely precise instructions being sent to individual qubits. A carefully timed pulse can change a qubit's state, place it into superposition, or prepare it for a quantum operation. So while a classical computer uses billions of tiny transistors switching on and off, a quantum computer relies on delicate qubits, extreme cooling, and precisely controlled microwave pulses. It's an incredible balancing act, and keeping all of this stable is one of the biggest engineering challenges in modern science. Now that we have our qubits sitting comfortably at temperatures colder than outer space, it's finally time to make them do something useful. After all, a computer isn't very helpful if it just sits there looking expensive. In a classical computer, calculations are performed using logic gates. These gates take bits as input and transform them into new outputs. Quantum gates have something similar, called quantum gates. But quantum gates don't simply flip a qubit between 0 and 1. Instead, they carefully manipulate the quantum state of a qubit. Think of a qubit like a spinning globe. A classical bit can only point to two locations, 0 or 1. A qubit, however, can point in many different directions, and quantum gates are the tools that rotate it with incredible precision. One famous example is the Hadamard gate. This gate can take a qubit that starts as a simple 0 and place it into a state of superposition. In other words, it prepares the qubit to behave according to the strange rules of quantum mechanics. But things get even more interesting when multiple qubits work together. This is where we meet one of the most famous ideas in quantum physics, entanglement. Entanglement creates a special connection between qubits. Once two qubits become entangled, they can no longer be described completely as separate objects. Instead, they behave as parts of a larger quantum system. And no, this doesn't mean they can send secret messages faster than light. Quantum physics is weird, but not that weird. What entanglement does provide is a powerful way for qubits to coordinate and share quantum information. By combining superposition, entanglement, and carefully controlled quantum gates, engineers can build quantum circuits capable of solving certain problems in entirely new ways. And this combination is what gives quantum computing its unique potential. Of course, there's one small problem. These delicate quantum states are incredibly easy to break, and that's our next challenge begins: quantum error correction.
At this point, quantum computers sound pretty amazing. They can create superposition, generate entanglement, and perform calculations using the strange rules of quantum physics. So why doesn't everyone have a quantum computer already? Well, there's one tiny problem. And by tiny, I mean one of the biggest engineering challenges ever attempted. Qubits are incredibly fragile. A little bit of heat, a small vibration, stray electromagnetic noise, or even tiny imperfections in the hardware can disturb a qubit's quantum state. Imagine trying to balance a pencil perfectly on its tip during an earthquake. That's roughly how quantum engineers feel on a normal workday. When a qubit loses its delicate quantum state, a process called decoherence occurs, and once that happens, valuable quantum information can be lost. Classical computers have errors too, but fixing them is relatively simple. Quantum computers don't get that luxury. You can't just make a copy of a qubit and save a backup somewhere. Quantum mechanics has its own rules, and they're not always cooperative. So researchers use something called quantum error correction. The idea is surprisingly clever. Instead of relying on a single qubit, information is spread across many qubits working together. If one qubit makes a mistake, the system can often detect and correct the error before the computation falls apart. The catch? You may need hundreds or even thousands of physical qubits to create a single, reliable, logical qubit. That's one reason today's quantum computers are still in the early stages of development. But progress is happening fast. Every year, researchers improve qubit quality, reduce errors, and build larger quantum processors. And while quantum computers won't replace your laptop, smartphone, or gaming PC anytime soon, they could become powerful tools for solving specialized problems in science, chemistry, optimization, and materials research. The future of computing is unlikely to be classical or quantum. Most likely, it will be both. Classical computers handling everyday tasks, quantum computers tackling problems that were once considered impossible. And this is only the beginning of the quantum journey.